Hi everyone. In this video, I plan to answer a number of select questions from the discussion board. I'm not going to answer all of them because I want to leave a few for you to answer for each other. In fact, I will probably only answer for about 10 minutes, I anticipate. So that's probably only going to allow me to get to 2, 3, maybe 4 questions. I'm going to preferentially answer questions that have thumbs up votes, likes there on the discussion boards. And I will also give preference to questions that seem to appear more often than others. Okay, Jeremiah asked this first question. What are the properties of H2O that allows the molar volume of the liquid to be less than the molar volume of the solid? I'm going to draw a picture here in a moment that will help illustrate why that is. So you've probably seen a diagram like this before. Over here, I'm depicting solid H2O. Notice that all of the molecules are lined up and arranged in very regular patterns. The effect that this has is to actually separate out the average distance between the molecules. When they fall into place, they push each other apart slightly. And you can see this. If you ever put a glass of water in the freezer, you'll see it kind of bulge up after it's frozen solid. And in contrast, this liquid H2O, the water molecules are arranged in random orientations. They're still very strongly interacting, so they're almost crystalline, but the fact that they can point in a number of different random directions, paradoxically, actually allows them to come closer together than they would in the solid state. So that is why the molar volume of liquid H2O is less than the molar volume of the solid H2O, and why a high degree of pressure will actually favor the liquid state and lower the freezing point for H2O. Okay, our next question is asked by Adam, and this one got 1 thumbs up so far. I really like this question. How are the phases of solids named? For instance, why ice 4 or ice 5? And the answer is, I actually don't know the answer to this question. I might have to ask Dr. Martin or another expert, although I very strongly suspect that it's the order in which they were experimentally discovered. So ice 1 is the form of ice that everyone already knows, and then ice 2, I actually looked it up, it was discovered in 1900, and then presumably ice 3, ice 4, ice 5 were discovered at various locations of the pressure-temperature phase diagram later on in time. So that at least is one possible explanation for the numbering scheme of the different solid phases. Okay, Kaylee asked the next question. What is the difference between P and P prime in the fugacity formula? Okay, if you look at the fugacity formula, the P is the pressure of the system and it is on the boundaries of the integral, whereas P prime is in the integral. And the difference is that P is the system's pressure, but P prime is a variable of integration. Here is an example of using something else as a variable of integration that you should be fairly familiar with. If I have a constant P external, then you know that the work is equal to an integral from V1 to V2 with a negative P external dV inside there like that. And let's say I knew that V1 was 1 liter, but I didn't know what V2 was. I could write this integral in a slightly different way. I could say from 1 liter to V, but then I'm already using V inside there for the variable of integration. So in this case, I could just say dV prime like that. That's really all that's happening. The difference is the variable without the prime is there on the integral, and the variable with the prime is the variable of integration. Okay, Gabrielle asked this next question. She asked to explain the weak versus strong interactions and the enthalpy of mixing. I'm going to draw a picture here in a moment to depict what I'm talking about. So as you can see right here, I've drawn a picture of 2 different substances mixing. So in an ideal solution, the strength of attraction between the two red particles is going to be the exact same force as between two blue particles, which is going to be the exact same force between a red and a blue particle. So same force. Another way to say this is no change in potential energy of mixing. So since the enthalpy is potential energy, the delta H of mixing is equal to 0. But if we have a strong energy of mixing, or enthalpy of mixing, all that means is if we have the two red particles and the two blue particles, they attract each other with a certain amount of force. But then, as soon as we mix the blue with the red, then we get a much stronger force of attraction between those two, like so. And so, in this particular case, the potential energy of mixing is going downhill of a sort, so it's decreasing because it's favorable for those two substances to be mixing. So therefore, since the potential energy is decreasing because we're moving in the same direction as the force, this delta H of mixing is going to be less than 0. It's actually going to be exothermic. Okay, the next situation is weak. So in weak energies of mixing, we again have our blue and red particles. They're attracted by a certain force, but then as soon as the red and the blue mix, they are going to be attracted with very, very weak little forces. So that actually means that mixing is going to be slightly energetically unfavorable. Okay? So in this case, the potential energy increases with mixing. Or, again, another way to say that is that delta H of mixing is greater than 0. So hopefully that helps you understand the difference between stronger and weaker interactions for the enthalpy of mixing. Okay, Adam asked this question: is the transition from liquid to solid always called freezing, or is there a different term? And the answer is that yes, it's pretty much always called freezing. I can't think of a situation where it would be inappropriate to call a liquid to solid transition freezing, so you could always call it that. However, I could imagine for, depending on the material, a subfield might consider a different word, like for instance, solidify or crystallize, something like that. Okay, here's the last question I'm going to answer tonight. This is from Nick. He asked, when do we use the virial equation of state? What advantages does it have that the van der Waal equation of state does not? Well, I don't know if I can give you a specific answer to when you would always use the virial equation, though you would probably resort to the virial equation if you found out that the van der Waals equation was not sufficient. I could imagine a situation where you were trying the van der Waals equation for your experiments and it was just not working accurately enough. Then you could resort to the virial equation because the virial equation is more accurate. And why is that? That's because the virial equation is an infinite series. So actually, it can describe any function. So you could have the weirdest, funniest looking function like this, where maybe you have the molar volume here and the pressure here. The van der Waals equation is definitely not going to describe anything like that. I mean, this is a bit of a silly example because, again, we've got this weird situation where increasing the molar volume would increase the pressure. So I'm just using this as an illustrative example. The point is that the virial equation of state can be used to match any function, whereas the van der Waals equation will only fit highly specific functions. So the virial equation is more general, is another way to think of it.